Hi everyone, welcome to webinar live coding and end-to-end ML model in just 45 minutes. I'm Omka Palika and today we are doing something different. No slides, no theory, pure live coding. You're going to watch me build a working machine learning model from scratch and you will see every line of code as I write. Okay, by the end of this session, you will have a trained ML model that actually works, beautiful visualizations, a Git notebook you can download and use, and understanding of the entire ML work. So here's the deal. We are using Google Colab, free, no setup needed. I'll code, you watch, and at the end, we do some question answers. Right? Let's start. So as we see, first we need we need to import some libraries for this purpose. This is what we call a setup. So for this setup, I would like to import pandas and numpy for data loading and data handling purposes. And we need pyplot for data visualizations and also Seaborn for data visualizations. And the next thing we do is model training, so machine learning. So for that, I would like to import from sklearn or scikit-learn, we can say. We need data sets because we from data sets we import low digits data set, and yeah, we need sklearn dot model selection, and we import train test split to split the data into training and testing. So we do data pre-processing for the data we pick. For that, we take standard scalar from pre-processing, and let us also import a linear model that a logistic regression, and also ensembling techniques for from ensemble. We import a random forest classifier, and definitely we need some metrics, right? So for metrics, we are catching up accuracy score, confusion matrix, and classification report. And just one more thing, we go with some warnings if needed, and from the warnings, filter warnings, type ignore, right? So for just some clarification, let's print it. All libraries imported successfully. So I just run it. It just connected to the runtime, and now it will load our cell. This is the standard ML stack we'll use. So something there is, oh, okay. It's ensemble, right? And let me run it. Right. So perfect. Everything imported. And now let's load the data, right? To load the data, so we are taking low digits data set from sklearn. So to load the data, these are handwritten digits from 0 to 9. So this is a small more data we gonna use it today. So I take a variable digits and I load it. I load the digits data set into this, and now I need X stores the digit data of the digits, and Y stores digits target from the digits. So what we do is, so from this, what we do is, so this data set, this disease data set has around 1797, like 1797 images, each of 8 by 8 pixels, having 64 features and labels of 0 to 9. So imagine you're building a postal service mail sorter and you have thousands of handwritten digits and you need a model that can read them. So this is how we work with the data, and yeah, so let's see what's the shape of this data. So we go with dataset shape. For that we need x dot shape. Okay, I need to use the formatting string. Right, perfect. So also, let us check number of classes we have. number of classes, unique values from Y. Let us see what classes we have. So we use NumPy again for this. Wait, NumPy unique of Y, and also we take what are the minimum features and the maximum features we need for this print um, features minimum x dot minimum and maximum x dot max. Yeah, see, until now we have, okay, there's some error here. Yeah, this this has to be added. So until now we are going to go. Yeah, see, we have 1797 of images with the 64 features. So number of classes we have as 10, and the classes are like 0 to 9. So the features minimum was 0 to 0 and maximum is 60, right? So now let's convert into data frame df, and we use pandas for data frame. So we need x, and what columns we need are let us say pixel for I in range for I in range of x dot shape. Right. Let us say we have digits column and we insert y to it. Done. So let us finally check whether the data frame is loaded and what's the shape of the data frame. So data frame shape df shape. So here, and let's see what this data frame is actually having. Let's check the first 5 rows of the data frame. Yeah, we are good to go now. See, Our data frame shape is almost the same as the dataset shape, and data. This is the data we have in our data frame. So 5 rows into 65 columns. Yeah, see 1797 samples, 10 classes of digits, all the 10 classes are digits of 0 to 9. Each pixel is a number from 0 to 60, representing the brightness. Let's visualize what one of these digits looks like. So we need to visualize how it actually looks, right? So let's visualize some samples. For that, let me take and access two variables, and I'm gonna use the matplotlib for this. So plt dot subplots to comma 5 comma and the fixed size. Let me go with 10:5 for a good for to fit the image in this window. And we're gonna enumerate the axis and the flat. So as in, let us take CMap gray and x dot set title. What it shows is digit, right? So digits of target and x dot show, sorry, axis of. And next, plt dot super title. So it's a sample sample written digits from dataset, right? Let us give it a font size of 14, font weight as bold. Next, plt dot, we need tight layout and show. There is some, okay, fixed size equals to. Yeah, here are the sample handwritten digits from the dataset. So for digit 0, digit 1, digit 2, digit 3, these are some samples that we have in the digits dataset that we loaded from SQL. Uh, when you can see here, so some are super clear. The, let us say, the 2, 4, 5, or the 0, some are super clear. This is the reality of real world data. Our model needs to handle all of them, even if they are clear or not. The model will learn if these pixels look like this, it's probably a 3. If they look like that, it's probably an 8. So let's explore the data a bit more. So we are going So we are going with data statistics in an Excel. So let us print class distribution. For that, I'm gonna take digits column from data frame and value counts. Let us sort its index. Done. So this is the class distribution. And let us check for some missing values. So let me print missing values. Df dot is null. And let us see how many we have. So I'm gonna use the sum function and again the sum to note the total missing values we have. As we can see, there are no missing values. We are safe now and we can continue with the next. So coming to the actual statistics. So let us print mean pixel value per digit. All right. So for this mean pixel value per digit, to have this, we need df dot, let's group by digit. As we said, we need mean and mean of columns also. So axis equals to 1. We have some error. So our error is like, let us write this again. So from data frame, we're gonna take use group by digit dot mean of axis equals to 1. So what I'm missing actually, key error, digit, didn't we mention the digit? Right, let us leave this here and we'll go with the rest. So the next step goes with the splitting of the data, obviously. So let us split into X prime, X test, Y prime, and Y test. So we're gonna use train test split from sklearn. We're gonna split the data into 80 to 20% again, and the random state goes with 42, right? Okay. So let us see how well we split the data. Training set. Xtrain dot shape. And next test set. And now we're gonna print the total. So Xtrain dot shape plus xtest dot shape samples. So we have total 1797 samples, and we split into 1437 and 360. 1437 samples goes to the training set, and the other 360 samples goes into the training set. Next, let us verify the splitting. So to verify the splitting, let me print training labels distribution. For that, we use series function from the pandas. We go with the ytrain and value counts and sort index. So for each training label, we have we have training tables where 0 to 9, and these are the number of samples we have for each training label. Next, we're gonna normalize the pixel values. Currently, it is 0 to 1, 6, right? So we need to normalize the values. So for that, I'm using scalar. I'm using standard scalar. Then Xtrain scaled. So we are going to scale the Xtrain data. I'm going to use scalar.fit transform on Xtrain data. And the next I'm going with on Xtest. So now let us check after scaling the print. Let's print the original first. So original text train, original Xtrain range. So original Xtrain range. So we have Xtrain dot minimum and Xtrain dot maximum. Then the scaled Xtrain range. Let us take up. Okay, fine. And the scale Xtrain. mean. Also, let's take, wait. So not just mean, let us also consider the standard deviation also. So we are using standard deviation function. So let us check. See, okay, the decimals are too long. So let us trim it to use up to 2 decimals here also, and here also as well here. Yeah, so we got an proper range now. So the original range was from 0 to 16. Now after scaling, we have -3 to 37.89, and the mean is 0 and the standard deviation is 0.98. So we can say that the features are scaled now. And let us check the scaled data. So we need to verify the scaling. So to verify the scaling, I'm gonna write the print statements. Training set shape and the set shape, test shape. So printing it, we have 143764 for training set and 36064 for test set shape, right? Now the actual thing we're gonna do is model training. So I don't want to waste much time on writing the codes for training and dataset. I'm gonna paste it and I'm gonna explain it to you. Let me paste the code now. Yeah, all these codes will be available to you on the notebook, right? So let me explain you this. Here we are going to train a logistic regression. Okay, we are starting with simple with logistic regression. Despite the name, it's a good for classification. Also, it's fast, interpretable, and often the baseline for comparison. So let us run this. Look at that, 97% accuracy on the test set. So that means out of 360 digits, the model has never seen. It correctly identified 349 of them. That's pretty amazing, right? So, but wait, can we do better? Let's try the next thing, random forest. So let me give you code for random forest. Let's try. And random forest is an ensemble of decision trees. So it's more complex, but often performs better. So wow, it's 97% again, maybe because the data is too small. So uh, remember, random forest is always greater than logistic regression for this task. But that's a whole deep dive for now. Just now, different models, different results will give you, and let's compare them again. So let's go for the model comparison. I'm gonna compare logistic regression and random forest. So both of them are having almost the same accuracy. So for now, we are having, let us take consider random forest as the better model for now. And next, the next important thing is feature importance. So for that, we are gonna plot some data. See, these are the top most important features from the data we have. So at pixel 21 from pixel 36 and all these things we are getting um, the percentage of importance, and this is the heat map drawn which pixel matters more. So look at this heat map. The red areas are the pixel the model relies on most. Notice they are in the center. That makes sense. So the edges are mostly empty spaces. This is why interpreting models matter. You're not just getting predictions, you're understanding how the model thinks. So next we can go with model evaluation and visualization. So to visualize and to evaluate model, we're gonna take confusion matrix. So this is the confusion matrix we get using this confusion matrix function, and we are using heat map from the seaborn, and here is the plot I drawn between the labels, the predicted labels and the true labels, and see, it is confusing a little bit at some points, but most of it is we have a good evaluation. Let us see some yeah. So let us see at 3 and let us see at 8. There is a bit confusion between 3 and 8. So or we can see the 4 and we can see the 9. Okay. So next we can go with classification report. This shows the precision, recall, and F1 score for each digit class. So from 0 to 9 classes, we have the precision, recall, F1 score. And out of predictions of 3, how many were actually 3? So this is what the precision gives you. And the recall gives you out of actual 3s, how many did we catch? And F1 gives you harmonic mean of precision and recall. We are looking at around 97% to 100% precision and recall across all digits, right? This is excellent. So let's go for visualization of model predictions. Again, we go with matplotlib. Let's visually inspect some predictions. Right. See, this is the true value and that is as the predicted value from the model. So the actual value is 6 and the predicted label is also 6. All of these were predicted well, and everything is green. So all are matching excellently. So you might see somewhere sometimes the red ones. So some red ones show that the prediction is actually wrong. So the model has confused between different different labels. So this is the power of visualization. Like we need to visualize whether everything is correct or not. Like we can't tell like having some theory of part, or we can give some note part. So we go for visualizations so that we can really uh, see, visuals are always greater than just text, right? So we're gonna get it much more easier to find the errors and everything by visualizing it. And let us go with learning curve. So how is it learning while training and while testing. This learning curve shows as we train on more data, both train and test accuracy improve. See how it plateaus around 1000 samples. So if it goes, see, from around 250 to 800 or around 1000, the learning curve for the testing is varied. So this is useful for knowing, do I need to collect more data, or if your curve is still climbing, yes, if it's flat, you're good. Okay. If the curve is flat, you're good. Or if it's just moving around, like if you have this curving, so it's actually learning more and we need to add more data. So let us make some improvement or try with different hyperparameters, and let us see which model gives you a good remark. So we are testing random forest. Okay, different random forest configurations. So I'm giving an estimate as 50, 100, 200, and 300, and maximum depth to 10 to and infinity. So let me run this cell first. So what are hyperparameters actually? Hyperparameters are settings like how many trees and how deep can they grow. Okay, so let's optimize. The model we trained was good, but maybe we can squeeze out even better performance by tuning hyperparameters. So interesting. Some configurations do slightly better than others, but yeah. So the overall best configure accuracy we are getting is 97.2. That is already we got without hyperparameter tuning. So experimenting might give you sometimes a better thing. How about training using gradient boosting? We all learned that gradient boosting is better than uh, other types, right? So why not try gradient boosting? So for the gradient boosting, I'm gonna paste the code here. See, I took the gradient boosting classifier and I'm trying the gradient boosting classifier. The let us see the accuracy of the gradient boost. Okay, it's taking a bit time to train the gradient boost. Yeah, done. So we got 96.94. So let us go for the final comparison. We have already tried logic regression, the random forest, and the gradient boosting. So out of all these three, both logistic regression and random forest gave the same result. So both were the winners. And with no late, we can save the model. So to save the model, we use pickle and JSON. So let us name it as best digit classifier, and let us run this. Scalar is not, where is okay. Let me run all of them again. Okay, it takes a bit time, but it obviously loads quicker. So it's here now, and we're gonna get here. Okay, for now, let's not save the scalar and go for the other. Yeah, the model is saved now. Until now, we are having the model, and also we saved the metadata, like what type of model we are using and what is the accuracy, the hyperparameters and feature count and everything. Okay, now we can directly use the model by loading it. So let me load the model and use the model. Okay, we are not using the scalar, right? So let's just go for, okay, here also we need to close. And anywhere else, right? The next line, prediction. Okay, here you. Yeah, and yeah, right. All these features, let us just close. Done. Yeah. So here we can see I'm using the first test sample, and for the first test sample, it is 6, and the image is like this, right? And yeah, we are almost at the end of the session. So let me give you a good summary about what we did today. So today we first loaded the data from my data set. We used a digits data set, and then we visualized some samples, checked distributions, and looked for some missing values. And then we pre-processed the data, and we trained the models, evaluated the models, and also tried to optimize the model using some optimizing techniques like hyperparameter tuning and all. And also we checked the learning curves, and finally we saved and deployed the ML model. So this is the entire ML workflow. You can repeat this for any data set, any problem. So the only thing changes is the data and possibly the algorithm. So which algorithm you go with, that will be the end. Here's what I want you to take away from this webinar. So ML is not magic. It's a systematic process. You can use the entire workflow in just 40 minutes. Sometimes it goes more time for based on the dataset size or the type of model you use. Start simple, then optimize. We started with logistic regression and then improved with random forest. Always visualize your results. Plots and confusion matrices tell stories, not just numbers. Okay? Save your models. Don't do all this work again and again, and just save your model. The hardest part isn't the algorithm, it's the data. Data cleaning, data exploration, and pre-processing takes 80% of the time in real projects. And the rest 20% is just the model building or model training. This notebook is yours now. You can check the description for this notebook link. You can download it, modify it, and use it for your own projects. And that's how you learn by doing. Okay. Let's meet again someday. And okay, let me give you some questions and answers for you. You might ask, why did you scale the data and what's the difference? So, some algorithms are sensitive to feature scaling. So, logistic regression and random forests aren't super sensitive, but scaling helps them learn faster. Neural networks are very sensitive. In general, always scale unless you have a reason not to. Okay, okay, next question can be, can I use this workflow on my own data set? 100%. Just replace low digits with your own data. If it's CSV, you can use read CSV function from the pandas, and you can read the file, and the rest of the workflows is identical. Another question can be like, what if my model accuracy is only 70%? First, check if it's worse than random forest, which would be 10% for 10 skills, 10 classes. If it's 70% plus, you're okay. To improve, get more data, engineer better features, or try different algorithms. Usually, more data helps most. Okay, next question can be, should I always use the most complex model? No, use the simplest model that meets your accuracy requirements. Why? Because simpler models are faster, easier to explain, and less likely to overfit. Use logistic regression if it works. Use random forest if you need better accuracy. Use deep learning only if simple model fails. And how long does it take to train models on real data? Depends on size. Small data sets like less than 100,000 rows can take seconds. Some medium like 1 million takes minutes. Larger means greater than 1 billion rows can take hours. This notebook is tiny. All models tiny, less than 10 seconds. Real projects take longer. Okay. So what is overfitting? When your model learns the exact training data too well and fails on new data, let me give you an example. Imagine a student who memorizes answers instead of learning concepts. Training accuracy is 99%, test accuracy is 60%. That's overfitting. Combat it with more data, simpler models, regularization. This student might fail in the test in examinations. Okay, as he just memorized his answer, but not learning the concept. If the question was something different, the answer might totally confuse him. So how do you know if my train test split is good? If train accuracy equals almost equals test accuracy, it is good. If training is very greater than test, or it possibly it causes overfitting, and if the train is less than the test, data inconsistency can probably give you a bug. So in this that notebook, both were 99%. So perfect. So can I do this in TensorFlow instead of sklearn? Yes, but overkill for this dataset because TensorFlow is for deep learning. For traditional ML, sklearn is the way to go. And TensorFlow would work, but is like using a sledgehammer to hang a picture. So what's the next step after this? Pick a real dataset. You can use Kaggle. It has the thousands of datasets. Run this workflow and improve. Or wrap this model in an API to deploy it, or just learn deep learning if you want to go fancy. Okay. And troubleshooting tips, if collab is slow, restart your runtime, use some GPU, and close other tabs. If your cell fails, read the error message carefully, Google the error, check for typos, make sure you run cells in order. And if accuracy is low, check your train test split, check for data leakage using test data during training, and try different algorithms or get more data. If you run out of time, skip cells like 16 to 19, you know, like optimization and saving, and focus on cells from first to the 15th, the core workflow. If you want to follow along, you can download this notebook or create your own collab and copy paste the cells, run each cell, and please don't just read it. Right? Done. So it's a very happy to go through this webinar today, and yeah, make sure to post on LinkedIn. Just finished a live coding webinar and to end ML in 45 minutes with the Data Valley, and also do follow my profile, and it's Omka Palika signing up. Thank you guys.